What's up, Michael? Thanks, man. Ooh, I think that's out of tune. What's up, Chris? Kevin used to play guitar a long time ago. Lost touch with it. Hey, this is the perfect time to reacquaint yourself. Have I seen the automatic tuners from Gibson? No. Does it go cool but not really useful? How are you guys doing today? Good. That's really out of tune. That's better. You should try E. Just everything E string? What do you even do with that? Think I should order that motor and get her did. I want to look at that motor a little bit more, Chris. Chica Nito has a song with just E tuning. I'm gonna write that down. Chica. What's the song called? I'll have to look that up. Oh. It's just fun to fiddle around. To just fiddle around on the guitar. Do you guys play any instruments? It's one way to stay sane. One way to stay sane during this time. Drums and the MIDI controller. I didn't know you played drums. Guitar, cello, and piano. Oh, very nice. I love the cello. I play viola. That was my first instrument. I only got into guitar maybe the past 2 or 3 years. But guitar is my favorite right now. Flute. Oh, very cool. Trumpet was my first. Always hated it. Yeah, I mean, if you're playing a brass instrument, it's like you have one volume, right? You can't just like chill around a campfire and break out the trumpet. Same with I guess viola is a stringed instrument like that is a little more accessible, but it still feels so classic. I don't know. Maybe I need to get back into that more. Just some relaxing evening trumpet. That's funny. Let's see. Maybe I can get some background going. That's not working. All right, you guys ready to get started for today? Let me turn off this night light. So today, we're going to talk about higher order systems. And by higher order, I mean like third order and higher. So far we've done first order, second order. I think we had a little bit of third order in one of the homeworks, but today I want to just formally discuss how we deal with higher order systems. And fortunately, it's not any harder conceptually than dealing with like a second order system, because we're going to see that higher order systems are just combinations of second order and first order systems like linked together. So you don't need any new techniques to deal with third order and higher systems, fortunately. So that's pretty cool. And I thought I'd start the day by introducing some physical examples. So where are these higher order systems going to come up in practice? So have any of you been to Taiwan? Specifically the city of Taipei in the north. I was lucky to spend a summer there maybe 4 or 5 years ago. And this is a building in the city of Taipei. It's called Taipei 101. 101 for the number of stories. Chris, I don't know what full moon party is. But something very interesting about this building, other than just being huge, I think it's one of the top 10 tallest skyscrapers in the world. It has this device. I can't remember now which floor it's on. Maybe it's like the 86th or like the 91st floor, but it's way up there. So maybe it's like somewhere like up here. And what this is called is a tuned mass damper. Tuned mass damper. And you can see this, it spans a couple stories of the building. You can, for scale, you can see like a person standing here. So when you go and visit Taipei 101, hopefully better. Oh, zing. Nice one, Michael. Okay, so if you go to the top, you can actually look at this thing. And it's massive. I used to have the spec sheet on this damper, but it weighs like hundreds of tons. It's massive. And it sits on these dampers. So kind of like those dampers we've been showing in these spring mass systems. And so the whole reason this thing is here at the top of the building is in Taiwan, there a lot of hurricanes blow through, earthquakes and the like, and that can cause huge vibrations of this building. So the purpose of this massive, dense, heavy damper is when the building wants to like swing one way, the this damper will swing the other way, and it'll create a force on the skyscraper that kind of stabilizes it. It's very cool. If you look up, we won't do this right now, but you can look up YouTube videos of people who were inside the building while an earthquake was going on, or I can't remember, but something big is going on outside, and people are standing here, and you can actually see this massive ball start to move around and to resist the larger motions of the building. So it's very fascinating. I suggest you check it out on your own time. But engineers had to decide, how heavy do we make this huge ball? And also, what should the 432 Park Avenue, we have dampers there too. Oh, very cool. And what should these damping coefficients be at the base? Oh, sorry, Phil. I blocked links being posted in the chat. So I found this paper. You can follow this link if you're interested, and they talk about some of the engineering design decisions that went into making this tuned mass damper. And here's a schematic of the skyscraper. And this is cool that people who build skyscrapers, those engineers, those civil engineers, they use these spring mass systems connected in series to represent all of the different floors being connected together. So like each of these represents a spring, and they use the coefficient K. And then they use a damper here. So any relative motion of the floors is met with some reaction force from a spring, and also a reaction force from the damper, depending on how quickly that floor is moving relative to the floors it's connected to. And this, at the very top, represents this tuned mass damper system. So this mass here represents the mass of that giant sphere, and then this represents the spring force and then the damping force. And this is a higher order system because each floor is a second order system, and when you add another floor, it adds another second order system, so on and so forth. So you do the math. If this is 101 stories, that's 101 second order systems. So that's basically a 200th order system. And this damper adds another spring mass system. So we're looking at what, like a 204th order system. And actually, maybe we'll do this next week or this week. Simulating the response of a system like this is not too difficult. And I've done that in this class before, so maybe we'll have to do this. But that's one of the cool things about showing you higher order systems today. You'll quickly realize that simulating, studying these systems, analyzing them, it's not outside of your grasp at all. Okay. Here's just another quick example. So when we do flight dynamics, one way to represent the equations of motion is with these three right here. I call them 1A, 1B, 1C. But these are three first order equations. I'll zoom in a little bit. You can see U dot, V dot, and W dot. So what we have here is a third order system, because these are three first order systems that are coupled together. Like you'll see this U dot equation, if you look on the right hand side, it depends on V and W. And here's like V dot and W dot down here. So these equations are coupled, they depend on each other. And if you do some substitution, it would be a nightmare to chain this into one equation with all these variables. But it's third over overall. And, what is U, V, and W? If you look at this, U represents the longitudinal speed. So if you're looking out the windshield of the aircraft, U is how fast you're going relative to the incoming wind. W is like your speed down. Hopefully that's not going too fast. And V would be the speed outside the right wing. So it's relative to that coordinate system, how fast is the aircraft translating in the sky relative to oncoming wind. So if you're working with these equations for an aircraft, it's third order. Aircraft equations, they can go higher order than this if you start including the angle of attack and its time dependency as a variable, the pitch rate, all of that. And you can get like 8th order, 10th order equations of motion for an aircraft. But third order is like kind of the simplest we can go. So if you become a structural engineer, roll, pitch, and yaw. Yeah, exactly. Those are 3 other degrees of freedom. So if you're doing dynamics out in industry, you're going to be working with some of these higher order systems. Okay. But my friends, here is the good news. Let's talk about the homogeneous solution of higher order systems. So here's the good news. The overall homogeneous solution, doesn't matter if it's 200th order, 400th order, is the summation of the homogeneous solutions for each root. So, in other words, A higher order system is built up of first and second order systems. So think of like first and second order systems as like the basic Lego pieces that we use to create higher order systems. So if you know how to write the homogeneous solution of a first order or second order equation, you can write the homogeneous solution of a higher order system. It is no problem for you to do. All right. But we're going to start today with two third order systems. A tale of two third order systems. One's going to be on the left and one is going to be on the right. And we're going to kind of analyze these in parallel because I want to point out a couple things. But let's start with this one on the left. You can see it's third order, third time derivative here, x triple dot. What's the characteristic equation? We're getting to the point where I don't think it's necessary for you to go through all of the steps to get to the characteristic equation. It's fine if you just look at the differential equation and say, oh, this term's third order, that corresponds to a lambda cubed. This one's second order, lambda squared. That's totally fine. And remember, the characteristic equation is for the homogeneous part. So even though I say this is equal to f of t, which is some forcing function for this system, when I find the characteristic equation, I set the right-hand side equal to 0 because it corresponds to the homogeneous part. If you find the roots of this system, I'll go over to MATLAB really quick. Let's clear this. This is the way we're finding roots at this point. If I have lambda cubed plus 7 lambda squared plus 24 lambda plus 18, I have three roots. Minus 3 plus or minus 3i and minus 1. And so you see, I have drawn these roots in the complex plane. So that's the imaginary axis, the real axis. And I colored these roots differently for a reason. Minus 3i. But those are our three roots. Why don't we look at this differential equation on the right as well? We'll kind of do these side by side so we can get the characteristic equation for this one the same way. If you solve for the roots of this, I'll skip going to MATLAB, but same way. So you can see what I did when I made these third order systems. I made it of a complex conjugate pair, so that's the blue roots, and then just a first order system, the red. And the only difference between these two third order systems is I interchanged the real parts of the roots for each system. So like the system on the left, the complex roots have a real part of -3. And the first order root has a real part of -1. So the system on the right, I switched that. Because we're going to analyze that effect here. Okay. The homogeneous solution. So just like I wrote on the other page, the homogeneous solution for this third order system is going to be the summation of the homogeneous solutions for the systems that make up this thing. So I'll stay consistent with the colors here. So, okay, the homogeneous solution, it's going to be the homogeneous solution of these blue roots plus the homogeneous solution of these red roots. So for complex conjugate roots, we have an exponent to the real part of the root, and then we have a cosine and a sine. And then we're going to add the homogeneous solution for that first order root, which is just an exponent to the value of the root, and we just have these coefficients out in front. Let's do the same thing for the system on the right. Okay. So this time, that first order system has a real part of -3. The complex roots have a real part of -1. But notice the frequency of these roots remains the same. And remember, that's because the damped natural frequency of a root is just equal to the magnitude of its imaginary part. So even though from the left and the right I switched where these blue roots are, their distance, their imaginary part remained the same. So that's why their frequency remained the same. However, the natural frequency of these roots did change. If you remember, the natural frequency of a root is its distance from the origin. So our natural frequency got smaller. Oh, okay, question for you. Let's talk about the damping ratio. So, do these blue roots on the left or the right have the larger damping ratio? So which one has larger damping, the left or the right? Okay, the same. Any other opinions out there? Chris agrees. I disagree. I disagree, my friends. Uh-oh. Because if you make an angle relative to the negative real axis, yeah. The damping ratio is equal to the cosine of the angle. So the smaller that angle is, the bigger the damping ratio. So the roots on the left have a higher damping ratio because that angle's smaller. Okay, so this is the homogeneous solution for these two systems. And the way you would get these coefficients, A1, oh, I made a little mistake here. These coefficients should be different numbers because A1 and A2 are definitely different. There should be 3 unique coefficients here. But to solve for A1, A2, A3, you would use the initial conditions of the problem. This is a third order system, so we would have 3 initial conditions that we need. But for the sake of moving along faster, in each of these problems, let's just assume that the initial conditions are such that A1, A2, and A3 are all equal to 1 for both systems. And what I did is I'm plotting the homogeneous solution. So the black line is the overall homogeneous solution. And remember, it's the summation of the blue and the red parts. So the blue corresponds to the complex conjugate roots. The red corresponds to that one real root. So like I can explain this one on the left. Let's see. A3 is equal to 1. So the red starts at 1, right? The blue, A1 and A2 are both equal to 1, but at time equals 0, which is over here at the left, the sign will be equal to 0, so we're just left with the cosine term, which is 1. So both the blue and the red parts start at 1, but the overall homogeneous solution is the summation of the two, and that's why the overall homogeneous solution starts up at 2, because it's the addition. So this black line at every point is the result of adding up the blue and red lines at every single time. Okay. So obviously the left and the right graphs look different. This one on the left, it kind of just decays down to 0. It doesn't have any oscillations visibly. The one on the right, however, it starts at the same place, but you can see it has some very clear oscillations to it. Let's talk about why. Like, why are these two different? Well, let's answer this question for each graph. As time works towards infinity, the homogeneous solution for this one on the left looks more and more like the red. So the first order component. You can see this black line. Eventually, it's right on top of that red line there. For this one on the right, it's different. As time goes to infinity, the homogeneous solution looks more and more like the blue. So the second order component. Does anybody know why? Why is it that this system on the left, the overall solution seems to look more like the first order system as time goes on, but this one on the right, the overall system looks more like the second order system as time goes on? Zeta is causing a faster settling time. Okay, zeta being the damping ratio. Okay, that's close. What is the settling time based on for a root? Natural frequency. Well, it's based on the product of zeta and the natural frequency, or the roots. Yes, the real part of the roots. So I know that the settling time of a system, so how quickly it approaches its final value, is equal to 4 times the time constant. And the time constant is -1 over the real part of the root. So if you compare the pictures on the left and the right, these two different third order systems, for the one on the left, you notice that the blue root settles faster. It looks like it takes between 1 and 1.5 seconds for the blue system to settle. And by the time the blue system is settled and it's at 0, the red system still has a long ways to go. It's not even, it's a little over halfway to 0 at 1 second. The overall homogeneous solution is the summation of the blue and the red lines. So once we get to about 1 second and beyond, blue has already settled and it's at 0. So when I'm adding up the overall homogeneous solution, the blue part's just adding 0. So the red is the only thing contributing. And that's why the overall solution just looks like the red. Same thing in this case. Like after about 1 second, red has already settled. So the only thing left is the blue. So that answers the question of why does the homogeneous solution start to look more and more like just one of the components rather than the other? This brings us to the important concept of dominant roots. So first, we'll write down the observation from that example up above. So as time marches on towards infinity, the homogeneous response of a system converges toward the homogeneous response of its slowest roots. And the reason that happens is because the fast roots go to 0. They get to that final value, and then they don't add anything anymore. So you're just left with the slow roots. That's why we call the slowest roots the dominant roots. Because they dominate the response eventually. They dominate the response as time marches on. All right, this has some important implications, which I'll show you an example for in a second. So one of these implications is when we model systems, maybe a skyscraper, we often ignore roots that are much faster than the dominant roots. Because you're not going to really see the effect of these fast roots in the overall system response. Because very quickly they go to 0, and then you're just left with the slow roots. So the fastest roots often don't play a major role in the overall system dynamics. And if we ignore these really fast roots, it results in a simpler model for us. Because let's say I have like a 20th order system, but
really it behaves more like a second order system if it has very dominant second order roots. I might just say, get rid of those other roots. It basically behaves second order. Let's just analyze it like that. It'll make our lives easier. Okay, let's do an example. So we're going to look at, so I'm going to start with this schematic to explain what's going on here. We're going to take a 2-cart spring mass system. And as we saw at the beginning of this class, you could use a model like this to model a 2-story building. And I'm going to draw one of these masses much smaller than the other, because if you look at these parameters up here, I said M1 is 1 kilogram, but M2 is only 1/10 of a kilogram. It's still connected via a spring and damper. And then we'll put another wall over here. Okay. Let's say that the movement of this first mass is x. And what I did in advance is I derived the differential equation for this system and I plugged in all of these numbers up here. And what you get is a 4th order differential equation. When you're looking at a mechanical system like this, the rule of thumb is that for each mass in the system, it adds 2 orders to the system order. So we have 2 masses here, 2 times 2. This is overall behaves as a 4th order system. So let's get the general homogeneous solution for this 4th order system. So I guess I skipped a step here, but your first step is you always get the characteristic equation for your system. So that's going to be lambda to the 4th plus 2.2 lambda cubed plus 22.3 lambda squared plus 6 lambda plus 30 equals 0. Boom, done. That's the characteristic equation. Then we're going to go over to MATLAB and get the roots. So roots of lambda to the 4th plus 2.2 lambda cubed plus 22.3 lambda squared plus 6 lambda plus 30. So you see that this 4th order system is a combination of 2 second order systems. I'm going to go back to my tablet and I'll write down those roots. So I'll call one set of roots lambda 1 and 2. That's minus 1.027 plus or minus 4.414i. So that's one pair. And lambda 3 and 4 are minus 0.073 plus or minus 1.206i. And heck, why don't we make a little miniature complex plane here. Let's see. 1, 2, 3, 4. 1, 2, 3, 4. 5. And then I'm going to stretch out this real axis a little bit. I'm going to make this like 0.2, 0.4, 0.6, 0.8, 1. But this imaginary axis is I, 2i, 3i, 4i. I know that's kind of crammed. Okay, but lambda 1 and 2 are at -1 plus or minus 4.4i. So they're like out here. And then lambda 3 and 4, it's at 0.07. So their real part is way over here. And the imaginary part is much smaller as well. So these roots are lambda 3 and 4. No, I messed that up. Those red roots are lambda 1 and 2. All right, so you can tell by looking at the complex plane here. The red roots have a higher damped natural frequency, so that's just the imaginary part of the root. They have a higher natural frequency, which is the distance from the origin. It looks like they have a higher damping ratio because they have a smaller angle relative to the minus real axis. They also have a much faster settling time. Why don't we calculate that? The time constant is -1 over -0.073. Oh wait, this should be blue. I'm mixing up my colors. Okay, we'll do that. Okay, so I guess we're looking at the blue roots first. I'm running over to MATLAB to crank that number. Okay, so the time constant for those blue roots is 13.7 seconds. So the settling time is right around 55 seconds. But if we look at the red roots, tau is -1 over -1.027 divided by 0.027. That's like 0.97 seconds. So the settling time is 4 times that, which is 3.9 seconds. Hello, Sika. Okay, so we see the red roots are much faster than the blue roots. And do we have dominant roots? Yes. The dominant roots are the slowest roots. Since the red roots decay so quickly, like in 4 seconds they're gone, there's like 50 seconds left just to the blue roots to decay. And so most of the time, the response is just going to look like the blue. So this is lambda 3 and 4 are the dominant roots. They are much slower. They are much slower. Let's write out the general solution here. And then I want to tell you physically what's going on a little bit. Okay, so the general solution. You guys can do this at this point. Remember, it's the summation of each of the parts. So I'm going to have e to the minus 0.073 t. I'll call it A1 cosine 1.2 t. I'm just kind of taking off decimal points here because I'm running out of room. So that's one part. And then I have to add the red roots plus e to the minus 1.027 t a3 cosine 4.4 t plus a4 sine 1.2 t. I'll put like a box around this so it's clear it's together. That's the overall homogeneous solution. So what you might do at this point as an engineer, you could say, look, I know this system is fourth order overall, but these red roots here, much faster dynamics. How about we just neglect that in our model and stick with the blue? Because that basically captures the essence of what's going on here. So I told you I would explain some of the physical stuff here. So there's what we call two modes of vibration for this problem. The first mode is where mass 1 and mass 2, they move with each other like in a synchronized motion. If mass 1 moves to the right, mass 2 moves to the right. And it turns out that kind of motion belongs to that slower blue root. The second mode is when the motion of these masses opposes each other. So they're out of phase. Like if mass 1 moves to the right, mass 2 moves closer. And actually, going back to the skyscraper example from the beginning, they try to build that damper to excite a mode 2 kind of behavior, so that when the building goes one way, the damper goes another, and they kind of oppose each other. So for this particular problem, the way I chose the masses, this mode 2 in the red becomes much less significant to the dynamics. And that kind of makes sense. Like if this is a really big, massive block, M1, if M2 was really small, it's really not going to throw off M1's motion. And M1 is just going to want to, go back and forth on its own. And it doesn't care what M2 is doing. Okay, so that's a fourth order system. It's got faster roots, it's got slower roots. Making the homogeneous solution is no problem, but I want you to be able to point out which roots are dominant and know what that means. So we won't go too much into detail with this, but a very similar problem to the one we just did is when you're analyzing the vertical motion of a suspension system. Say we have a road surface like this. You have your tire. You have your sprung mass. Let's just draw it like this. So you have like a spring, you have a damper, and these help to absorb some of the forces between the road and the car. Now it turns out, as you can imagine, the tire itself is a little springy, and you could imagine there being springs here as well. But often when we're simulating the bulk motions of a car, we ignore the stiffness and the reason is that the settling time of the tire dynamics are really, really quick relative to the dynamics of the bulk suspension system connected to your chassis. So because the tire dynamics, they're always going on, but because they're so much faster and lower amplitude and so on, we throw them out. This looks like a little face right here. Isn't that adorable? Okay, I'm getting rid of that. So we won't go into detail on that. That's just another quick example. Ooh. Guys, we're having a little bit of a shorter lecture today because all we have left, all we have left is this seventh order system example. So what I still want to do, it does look like that face. So what we're going to do is we're going to take a 5-minute break, and then we're going to come back. We're going to do that example, and then we'll end a little early. Sound good? So I'm going to come, I have 3:08 p.m. Eastern right now. We're going to resume again at 3:13. Try to get these tunes going again. Oh, there we go. Now it's working. Be right back, guys. we have an example to do. And that's going to close out our lecture today. Are you guys back? Are you ready? Let's get started. We have a 7th order system here. But at this point, I think nobody should be intimidated by that. A 7th order system in itself. Because we know how to deal with it. So let's first get the general form of the homogeneous solution. So to do that, we need to get the characteristic equation. Lambda to the 7th, 18 lambda to the 6th, 144 lambda to the 5th, 688 lambda to the 4th, 2180 lambda cubed, 4584 lambda squared, plus 5760 lambda, plus 3200 equals 0. So just by looking at the differential equation, we can quickly write the characteristic equation. Getting the roots, we allow MATLAB to do the grunt work. So 1 lambda to the 7th, 18 lambda to the 6th, 144 lambda to the 5th, 688 lambda to the 4th, 2180 lambda cubed, 4584 lambda squared, 5760 lambda, 3200. And we have 1, 2, 3, 4, 5, 6, 7 roots. I'm going to go back to my tablet, but I'll write down what all of these are. So, lambda 1 and 2, minus 1 plus or minus 3i. Lambda 3 and 4 just equal minus 4. So we have repeated real roots there. Lambda 5 and 6, minus 3 plus or minus I. And lambda 7 is minus 2. Now I want you, before I write this, I want you to take like a minute and based on those roots, write out what you think the general homogeneous solution is. So I'll just give you a minute. It's good to do things like this, practice, and then this is a chance to get immediate feedback because I'll write down what I get as soon as you finish. I love the summer. I hate the mosquitoes. I have a bite on my ankle that itches. All right. Actually, let's write it down here. I'm just going to go through each of these roots. So this is for lambda 1 and 2. All right. Let's do the contribution from lambda 3 and 4. And I guarantee a couple of you missed this critical detail. Or maybe you didn't. Prove me wrong. For this term, we need a t down here. Did you remember that? Anytime you have repeated real roots, you don't just write a3 e to the minus 4, a4 e to the minus 4. You need a t on one of those. That's what I'm talking about, Michael. Okay. So that one's a little tricky. All right, let's move on to the next. E to the minus 3t, a5 cosine t plus a6 sine t. And we're almost there. We just need plus a7 e to the minus 2t. And that's it. The overall homogeneous solution is a combination of the homogeneous solutions of each of the contributing parts. You could do that for a 100th order system. No problem. All right, let's define the system settling time. You got it? Very well done. Let's get the system settling time. Remember, this is based on the slowest root, which we now have a new name for, the dominant roots. Slowest means the dominant root. It dominates the response. How do we find the slowest root? You look at the real part of all of your roots. And you look for the root that is closest to the imaginary axis. Or in other words, it has the smallest real part. So these are our slowest roots. So lambda 1 and 2 are dominant. In other words, they're the slowest. And so we know that tau is minus 1 over the real part of the root, which is minus 1. So it's 1 second. So the settling time is 4 times tau, so it's 4 seconds. Okay, next task. Part C says, if the dominant roots are complex, which they are, calculate the damped natural frequency damping ratio, and natural frequency of the roots. Well, I think at this point, the best way to calculate those quantities is that geometric approach of putting these roots in the complex plane. So this is -1 plus or minus 3i. Okay. 1, 2, 3, 2, 3. All right. So the damped natural frequency is just the imaginary part of the root. So that's the easiest one. Omega d is going to be 3 radians per second. The natural frequency is the distance of the root from the origin. So we just have to use the Pythagorean theorem. It's going to be the horizontal side squared plus the vertical side squared, square root of that whole thing. So that's going to be the square root of 10. And that can't really be simplified anymore. I guess we can just get a decibel number for it. Square root of 10. 3.16. That's pretty close to pi. All right. Damping ratio. We find this angle with the negative real axis. We have to take the cosine of that angle. So the damping ratio is equal to the cosine of that angle. And that's going to be this adjacent side length, which is 1, divided by the length of the hypotenuse, which is just the natural frequency. And that gives us 0.316. Easy. We're just cruising along today. Okay. The last part. Let's find the particular solution if f of t is 100. So f of t is this forcing function to this 7th order system. So we're saying, what if f of t is just 100, a constant? So now we're doing a little review. Because on Wednesday of this week, I want to do backwards and forwards particular solutions. We're going to master particular solutions. So okay. Let's go down here. So we're finding the particular solution if f of t is just 100. It's a constant. Okay, remember this. The particular solution is always of the same form as the forcing function itself. It is the same form as the forcing function. And we'll find on Wednesday, as well as the derivatives of the forcing function. So not just the forcing function, the particular solution is equal to it's the same form as the forcing function itself plus the derivatives of the forcing function. But fortunately, for a constant, the derivative is just 0. So we don't even have to worry about it. So, but using that rule, I'll say the particular solution x sub p is just equal to d, which is, just to be clear, it's a constant. 0 is my favorite number. Why is that? My favorite number... probably an 8, but I don't even know why. Okay. So, next step, sub your particular solution into the particular portion of the differential equation. So many reasons. It's so simple yet so complex. True. You can't divide by 0. It's undefined. It's the particular portion of the differential equation. I'm not surprised 0 is your favorite number, Chris. It's a very philosophical number. Okay, so this is a 7th order differential equation. And if my particular solution had up to 7 derivatives, I'd have to plug in every term up to that point. But even the first derivative of this d dt of a constant, it's equal to 0. So fortunately, I'm just going to have to plug in for the 0th order term in our differential equation, which I'd have to scroll up to even remember what that was. So we can only plug it in here because our particular solution would be 0 even at the first order and any other higher order derivatives. So I'm going to have 3200 x particular, which is 3200 times d, is equal to f of t, which is just 100 for all time. So that means d is 100 over 3200. Zero is the least lonely number. Also, it wins all of the pie eating contests. Because it looks like an open mouth. And remember, the overall solution, if you have a forcing function, it'll be the homogeneous plus the particular. So you would take that big 7th order homogeneous equation we wrote, and if there was a forcing function of 100, we would add this at the very end, and then we'd be left with our complete solution. And that's it, guys. So we're wrapping up a little bit early today, but I think we did justice to looking at how to approach higher order systems. We know how to get the general solution. We know how to pick out the dominant roots. We did a little bit of review of natural frequency, damping ratio, settling time. So I hope you feel good and confident about it. Will there be a homework for this lesson? Yes, there will. I'm going to upload that tonight. I don't think it'll be too extensive. You need to jump under. Ugh. Oh yeah, because you said you blew out your transmission, right? Dang. Yippee, fun, fun. Have you ever replaced a transmission before? And guys, I think what I'll do, waiting for parts shipping tomorrow. Usually we have office hours from 4 to 5. But why don't we just start now? We don't need any dead air time. I'll hang around here till 4:30. I'll try to get... I'll see if I can get that homework up in that time window. You actually did an auto to 5-speed swap? Wait, so you had a car with automatic transmission and you turned it into a manual? That sounds pretty impressive. Wow. Stage 5 unsprung clutch. Sucked for city driving. Is this an actual class? If so, I hope it's okay that I join. Kronborg, you are more than welcome to join. We're just wrapping up for today, but we meet every Monday, Wednesday, Friday from 2 to 4 Eastern US. We're just finishing up a little bit early today. All right, see you, Phil. Chris says, I have a question from a peer. We are building a wind tunnel. Do you have any sensor knowledge that'll be relevant? Well, what are you measuring in a wind tunnel? Like relative air velocity? Don't you use like a pitot? Or wait, pitot tube measures pressure. I'm not really like a fluids guy. Drag, okay. Drag, you're gonna need a force transducer, right? You know who you should talk to Matt Burge about this because he does the aerospace lab. And I know he I think it was in the fall, he had people taking wind tunnel measurements. But I'm not sure what force transducer he was using. I think they use like a 6-axis, let's see, 6-axis force transducer. Those are expensive though. Yeah, they're like a couple $100. Even a couple grand. I'm going to put up the notes. We were hoping to find a cheaper solution, perhaps something we did in MAE lab of some sort. Oh, so you're just making... How big is this? Like, what are you using this wind tunnel for? Small? But what does that mean? Like, is it... Like, what are you calculating the drag for? Desk size, hopefully the walls and objects we can suspend. What is this? Oh, this doesn't really show anything. Somebody was saying they did a custom... Oh, look at this. This is like a strain gauge that we would have used in Lab 1. So it looks like these guys just took this load cell and then mounted their... Yeah, they took 2 load cells. One to measure the drag, one to measure the lift. Maybe I'll send this link. You're very welcome. And those load cells are dirt cheap, man. Yeah, this one's $8. Gonna post the notes. Let's see. Chris, let me know what you think about the motor when you get a chance. I'm definitely looking forward to seeing this pendulum in action. Oh, I agree, man. You have a great day too, Chris. Yeah, I'll check that out. Thanks for looking into this. I'll check out this motor. Hey, just dropping by. Are non-students of yours welcome? Certainly. You are very welcome. We we have class Monday, Wednesday, Friday from 2 to 4 Eastern. So today we already wrapped up with the content. I'm just hanging around to take questions for another half hour or so. But yeah, you're always welcome to tune in. I hope you do. I hope you enjoy it. We're doing system dynamics. So all kinds of stuff about how things move and how we analyze it, how we model it. So system dynamics is vague. Can I expect to see Lyapunov exponents, etc.? We're exclusively working with linear systems. So what you're gonna, like Wednesday, we're gonna go over particular solutions of linear differential equations. I think Friday we'll go into linear state space representation. We're gonna talk about transfer functions, frequency response functions, Bode plots, modeling of electromechanical systems, the root locus. So it's like linear system dynamics. That would be like the predecessor to continuous control systems theory. Is there a generalization of transfer functions to MIMO systems? Yeah, sure. I think in that case you get a transfer function matrix. So the easiest way to get that transfer function matrix is to first get your system into a state space form. Have you worked with linear state space? And then like your state space or your transfer function matrix would be, I only dealt with MIMO by decoupling. Maybe I can send you a link for that. Yeah, basically what I sent is... Yeah. This is like your transfer function matrix for a MIMO system. You're coming from control engineering, so I can decouple the dynamics and just get two normal transfer functions instead of a matrix. Sure. Well, I mean, even if you have a transfer function matrix, each transfer function relates one of your inputs to one of your outputs. Wait, so am I answering your question? Now I'm confused. Confused if I gave you what you wanted. Oh, okay. Good to know. I've been trying to make a self-balancing robot, but I keep putting it on hold. This guy. I love control systems theory, but I'm trying to work on applications right now, like little simple. Well, this isn't simple though, but you get the idea, like little demos. Yeah, that's not linear, but I'm linearizing it. I mean, at least as a first cut. I like that because it can, like you said, you can apply a lot of nonlinear techniques. But first, I'm starting with linear. That'll be the easiest to get working, and then I can expand on it. Yes. No, but I mean, that is what I'm doing. I'm doing a small angle assumption. And then hoping that it works about that small operating range. Which, that's how a lot of these self-balancing robots do work. Many of them are just using basic linear controllers. Is linear control that much easier than model predictive control? I haven't done too much with model predictive control. But yeah, a linear controller will be easier to implement than MPC. Are you aware of techniques like PID controllers applied to PDE system? So you're just asking if PID has been applied to PDEs? I'm sure it has. But even like take a flexible beam or something, which fundamentally is a PDE, right? But even then, for control, I think you would represent that flexible beam with either a finite element model, or you would use like the assumed modes method. And in that case, it just reduces to an ODE. So I guess my answer is, in applications, at least that I'm familiar with, you would convert the PDE to an ODE. But maybe there's applications where that's not possible, or you wouldn't do it. I don't know, I feel like you would always do some kind of discretization. PIDs operate on a discrete number of control inputs. Are you aware of cases where the control is not a vector of scalars, but a function of scalars? Do you have like an example? Operate on a discrete number of control inputs. Okay. It's not a vector of scalars, but a function of scalars. So are you saying you have multiple inputs, but like are these scalars you're referring to each a control input themselves? Okay. Okay, so you have a pool with many, many small pumps along one side. You control the pump speed of each of them to shape the wave behavior. Instead of taking each pump as a single control variable, it might make sense to think about a function of pumping intensity along the border of the pool. So are you saying you have many pumps, but you're trying to express your control input as something like pump intensity? So it's kind of a combination of other inputs? The position of each pump is an interval, isn't it? If you take how far along it is on the pool border. I guess it's not totally clear to me right now how you're relating each pump to this pumping intensity. The position of each pump is on an interval, isn't it? And each pump does a certain amount of pumping. Wait, I have an idea. And my idea is a drawing. Okay, so you're saying you have a pool, and then along the side let's make it simple though. Like, let's say you have 3 pumps and each of these, I don't know, maybe it's like a motor and you control the speed. So you could have like speed of 1, speed of 2, speed of 3. And like you said, you could define some coordinate along the length of the pool so that each pump is located at some spatial point. Woo! What happened to the music? Okay. So help me understand. To shape the wave behavior. So you could, I don't know, drawing a curve of pumping density over X. Pumping density though, physically that, I don't know if that makes... I mean, each pump, maybe it produces a pressure. So maybe you mean like a pressure distribution along X or something? I don't know. So you have like a desired... Wait, so you have like, you said there's like a wave behavior you want, right? Imagine we take really small pumps and stick them together really, really close. Okay. I was just trying to simplify this by having like 3. But you're saying, okay, there's many pumps along here, each with their own speed. And I guess the local pressure is a function of that speed. Then if we chart how much each pump pumps over X, we get a function of X. Okay. So are you basically, and then the goal of these pumps is to affect some like 2-dimensional wave behavior here. So maybe that wave is a function of, wait, we should say like, that's X, that's Y. So the wave is a function of like X, Y, T. And this function is my control input. So you're saying like the wave behavior across this 2-dimensional space as a function of time is equal to this pressure distribution also as a function of time. Maybe we need a slightly different example. I get it. It's not good enough for you. I always say start simple though. If you can think of like the simplest illustration of what you're talking about, that might be our best bet. That sounds even more complex. We want to control cloud formation in the atmosphere to increase the reflectivity of the Earth. Okay, let's take a step back. And I have to go in 5 minutes, by the way. However, it sounds like you're asking a mathematical question. And you're trying to illustrate that mathematical question with some like physical problem. But I think the more complex you make the problem, the harder it is to just talk about a mathematical idea. I mean, I see you're getting at a controller. Yeah, sure. You have a control input which is spatially distributed. I even think this pool example shows a spatially distributed control because these pumps create a pressure distribution along that length of the pool, and that pressure distribution can change as a function of time. I don't see why this example is inadequate for describing a control input which is spatially distributed. Why was this example inadequate for that point? I guess is my question. Because here I have my system equation, which is generally non-linear, perhaps. It's a function of space and time. And then I'm applying an external forcing function, which is spatially distributed. How is this not what you're asking for? It works, but it is spatially distributed along one dimension. I thought that was causing some misunderstanding. Oh. Well, no. I think that's, I could make that clearer. I see. I mean, does it... I mean, you could... You could even change this example so that you have pumps along a different dimension of the pool. But I mean, is all you're getting at that you're saying like this function could be also covering the whole two-dimensional space? It's not just one dimension. Yeah. No problem. No, it sounds interesting. I mean, I'm sure there has to be literature on this, because the types of problems you're talking about, certainly people are thinking about them. I mean, even atmospheric control. I took a course in graduate school on environmental fluid dynamics, and I mean that applies to a lot of things, but it was dynamics of clouds and whatnot for like predictive weather models. And I'm sure people have applied control theory to that. What are those okay, control theories, climate model. Yeah, I mean stuff like this, model-based design, optimal multivariable climate control systems. That's boring. Cool, have a nice day, man. All right, everyone, I'm going to call it for today. I basically have a PDA where my control input is the boundary condition. Great. Well, good luck to you, my friend. We'll be back here on Wednesday as well as Friday. I hope you guys have a lovely afternoon. I've enjoyed spending time with you.